Hi, welcome to this video. Today we'll be talking about moments. Moments are a fundamental concept in math, physics, and engineering, and are something we use every day without thinking about it. There are a lot of different kinds of moments. There are moments of mass, moments of area, moments of really any type of quantity you can think of. The type that we'll be focusing on in this video are moments of force, which are also known as torques. The terms moment and torque are often used interchangeably, and that can be confusing, especially if you're just learning about them. Both refer to the idea of a force multiplied by a distance. In my field of structural engineering, moment is used more frequently, so that's the term I'll use. In this video, we'll start with a hands-on example to help you get an intuitive feel for what moments are and how they work. Then, we'll build on that example by identifying some defining characteristics of moments. After that, we'll walk through a couple common thought processes to calculate moments created by angled forces. And finally, we'll work out an example problem using each of those processes, putting some actual numbers behind the math. To start, let's dive into our hands-on example. A good way to experiment with moments is by opening and closing a door. If you've got a swinging door nearby, give this a try. Put your hand at the edge of the door, far away from the hinge, and push. Notice how the door swings open easily. Now, place your hand just a few inches away from the hinge and try to push the door open again. The door doesn't open as easily as it did before. It takes more effort, more force, to open the door when you push close to the hinge. Pause the video and play around with this for a minute. Feel how where you push on the door affects how hard you have to push. We find the reason for this difference in how moments, force, and distance are related. That relationship goes back to what I mentioned right at the beginning of the video. A moment is a force times a distance. This equation is a mathematical definition of a moment. A more intuitive definition is that a moment is the rotational effect of a force. When you push on the door, you apply a force at some distance away from the hinge of the door, creating a moment. The bigger the moment you create, the faster the door will swing open. You can apply a bigger moment to the door in one of two ways. Either push harder, increasing the force, or push farther away from the hinge, increasing the distance. The more distance there is between your hand and the hinge, the less force you need to open the door. That's why most doors have the handle far away from the hinge. So now we know the two key ingredients for a moment, a force and a distance. Let's look closer at each of these parts. Forces are pushes and pulls. They have a magnitude and direction, so mathematically we can think of them as vectors. That's why we typically show them as arrows. If there's no opposing force, forces create linear acceleration. Since moments are created by forces, they have a lot of similarities. Moments are like a twist instead of a push or pull. Like forces, they're vectors with a magnitude and a direction, and they create rotational acceleration if there's no opposing moment. The bigger the moment, the more rotational acceleration that moment creates, and the direction of the moment determines the direction of rotation. Now let's take a look at the distance part. Before we can measure a distance, we need some reference point to measure from. You can pick any point you want as your reference point. The point you pick will depend on the moment you're interested in looking at. For the door example, we're interested in how the force you apply to the door makes the door rotate. Since the hinge is the center of rotation for the door, that's a good spot to use as the reference point. The distance from the reference point to the force has a special name. It's called the moment arm. The moment arm is the shortest distance between our reference point and the line of action of the force. The line of action is the line in space where the force lives. The moment arm is always measured perpendicular to the line of action of the force. That's really important to remember, and you'll see why here in a bit. To see how these parts of a moment come together, it's helpful to have a way of visualizing the math behind moments. A good way to picture the size of a moment is using areas. This is the equation for the magnitude of a moment, with F being the size of the force and D being the length of the moment arm. Let's draw a rectangle with a length equal to the length of the moment arm and a width equal to the size of our force. The area of this rectangle represents the size of the moment. Now the rectangle shows us what happens to the moment as we move and change the force. If we slide our force farther from the hinge, the moment gets bigger. If we slide the force closer, the moment gets smaller. If we make the force bigger, the moment gets bigger. And if we make the force smaller, the moment gets smaller. This covers the magnitude part of the moment. We also need to note the direction. For the moment arm method, it's common to determine the direction of the moment by inspection. If the force makes an object rotate counterclockwise about the reference point, that's a positive moment. If it makes an object rotate clockwise instead, that's a negative moment. That comes from the right-hand rule sign convention, which is commonly used in math and physics. Basically, if you curl the fingers of your right hand in the direction of rotation and stick your thumb out, your thumb will point in the direction of the moment vector. If you get a thumbs up, it's a positive moment, and if you get a thumbs down, it's a negative moment. So the defining characteristics of a moment that we need to know before we can calculate it are what reference point we're measuring from, how long the moment arm is, how big the force is, and what way the force is going. Once we know these things, we can determine the size and the direction of the moment. One other thing that's worth covering before we dive into an example problem are angled forces. These were tricky for me when I was first learning about moments. We've seen how sliding the force along the door changes the length of the moment arm. Tilting the force at an angle also changes it. Go back to the door and try pushing on it at different angles for a bit so you can feel this. Notice how when you push at an angle, it takes more force to open the door. There are a couple of different ways to think about what's going on here. One way is to focus on the distance and what happens to the moment arm when we tilt the force. This is when that bit about the moment arm being perpendicular to the line of action of the force becomes important. Tilting the force like this shifts the moment arm away from where the force is applied, making it shorter. Now, even though the size of the force hasn't changed and where it's applied on the door hasn't changed, the line of action of the force passes closer to the hinge, so it creates a smaller moment. Another way to think about why the moment gets smaller is to focus on the force. The tilted force can be broken down into two parts or component forces. One that's perpendicular to the door, contributing to the moment, and one that's parallel to the door, pushing through the hinge. When a force pushes directly through the hinge, it doesn't make the door rotate because the moment arm of that part of the force is 0. This means that for calculating the moment, we can just use the perpendicular part of the force. Let's jump into an example problem so you can see these ideas in practice. Say you're a mechanic working on a car. You need to loosen a bolt in the cramped engine compartment. Because of space restrictions, you can only get a 4-inch long wrench on the bolt, and from where you're working, you have to pull at an angle of 30 degrees down from the wrench. To loosen the bolt, you need a moment or torque of 30 pound-inches. If you pull with 20 pounds of force on the end of the wrench, will you loosen the bolt? If not, what needs to change? Let's start by simplifying this picture down to a free body diagram and filling in what we know. The bolt will be the center of rotation that we're interested in, just like the door hinge was earlier, so that'd be a good reference point to use for this problem. The wrench will be the bar we pull on to create the moment. That has a length of 4 inches. We have our force of 20 pounds pulling down at a 30-degree angle applied at the end of the wrench. Our goal is to calculate the moment and see if it will loosen the bolt. Since this problem has an angled force, we'll walk through both the force and distance approaches so you can see how they both work. I encourage you to pause the video and try applying what we've gone over so far to this example problem yourself. The best way to learn something is by doing it, and thinking through how to apply new principles and discovering how they work for yourself will help these new ideas stick for you. Once you've given it a try, come back and we'll walk through each method together. Let's use the distance approach first. The first thing we need to do is solve for the length of the moment arm. The only dimensions we were given in the problem statement are the distance from the bolt to where the force is applied and the angle between the wrench and the line of action of the force. We also know that the moment arm is perpendicular to the line of action of the force. This right angle means that we can use trigonometry to find the length of the moment arm. Each trig function takes in an angle in a right triangle and spits out the ratio of two sides of the triangle. Since the right angle in this triangle is across from the wrench, the length of the wrench forms the hypotenuse of the right triangle. We're looking for the moment arm, which is opposite to the angle we were given. So we need the trig function that relates the opposite side and the hypotenuse. A handy mnemonic to remember which trig functions match up with which ratio is SOHCAHTOA. The first triplet, SO, is the one that we need here. The sine of the angle is equal to the opposite side divided by the hypotenuse. Plugging our angle and wrench length in, we can solve for the length of the moment arm. In this case, the moment arm equals 2 inches. Now that we have that, we can multiply the size of our force by the length of the moment arm, and we find the size of our moment to be 40 pound-inches. That's bigger than the 30 pound-inch moment that we'd need to loosen the bolt, so the moment is big enough to do the job. Now we just need to check the direction of the moment. Remember the right-hand rule that we discussed earlier? Bolts follow that convention too. If you curl the fingers of your right hand in the direction the bolt would turn, your thumb will point in the direction the bolt will move. Pulling on the wrench this way would make the bolt rotate clockwise. Using the right-hand rule, your thumb ends up pointing into the screen, away from you. This means that the bolt will actually get tighter instead of loosening. So, we need to change the direction of the moment. The easiest way to do that is to switch the direction of the force, pushing on the wrench instead of pulling on it. That gives us a positive moment of 40 pound-inches, which is both big enough and in the right direction to loosen the bolt. Now let's look at the same problem using the approach that focuses on the force. This is the approach I've seen used more frequently in practice. Again, the mindset for this approach is to break the force into 2 smaller forces, one perpendicular to the wrench, creating the moment, and the other parallel to the wrench, pushing through the bolt so that it doesn't create a moment. Let's call the parallel component Fx and the perpendicular component Fy. We can picture these 2 component forces creating a right triangle with the original force. Making a copy of these off to the side for a minute and sliding Fy over, we can see this right triangle more clearly. The component forces can't be bigger than the original force, so the original force has to form the hypotenuse of the right triangle. Now, we can use trig to find the size of Fy, which is what we need to determine the size of the moment. Fy is opposite to the 30-degree angle, and we know the original force is the hypotenuse, so we can use the sine function again. Solving for Fy, we get 10 pounds. Now, we can multiply Fy by the distance from the hinge to where it's applied to the wrench, and we get 40 pound-inches. This is a big enough moment to loosen the bolt, and now that the force is pushing on the wrench, it's going the right way to loosen the bolt. So, whether you focus on the distance part of the equation and solve for the moment arm, or focus on the force and break it into components, you'll arrive at the same answer. Depending on the problem, one approach may work better than the other. If you have a good way of directly measuring the moment arm, go the distance route. If that's not the case, it may make more sense to go with a component force option. And if you solve it one way and are unsure if you got it right, you can always try the other approach to double check. If you get the same number both ways, you're probably on the right track. Now that you're familiar with the fundamentals of moments and have a little bit of practice under your belt, working through a few problems on your own is the best way to get these ideas to sink in. I encourage you to find some other moment problems so you can get some practice. This concludes our overview of moments and how to calculate them using the moment arm method. If this has been helpful to you, please give this video a like and share it with someone else you think could use it. If you have any questions, please let me know in the comments and I'll do my best to answer them. And if you're interested in learning more about topics like this in structural engineering and related fields, please subscribe. Thanks for watching. See you next time.